Welcome to Study Loop.
So in this problem we are given with the decomposition reaction of PH3BCl3, which gives us PH3 and BCl3, and we are given the equilibrium constant in terms of pressure for this reaction. We are given the temperature, and at the first part of this problem we have to find out the value of Kc, that means equilibrium constant in terms of molarity. So we know that there is a relation between Kp and Kc, which is Kp is equal to Kc times RT whole bracket to the power del n. So here R is the universal gas constant, T is the temperature, delta is the difference between the gas number of gaseous molecules in product sites and reactor sites. So from here we can write down, so we can rearrange it as Kc equal to Kp over RT to the power del n. And if we just plug in the values, so the value of Kp is 0.052, R is universal gas constant 0.0821 times the temperature 333 for del n. The value of del n here will be, so in product side we have two gaseous molecules, 1 plus 1, and in reactant side we have 0 gaseous molecules since the reactor is a solid. So the value of del n will be 2 minus 0 equal to 2. So we have to put it 2 here, and solving this we can find the value of Kc, 7 times 10 to the minus 5. So this is the value of Kc for this reaction. Now, the second part of this reaction, we have to find out the equilibrium concentration of pH3. So to find out the equilibrium concentration of pH3, first we have to know the initial concentration of the products PH3 and BCl3. So now if we assume the molar solubility of the reactant as X mole per liter, then we can write down the initial concentration of both the product gases as X mole per liter or X molar, and for BCl3 also it will be X molar. Now we have to calculate the value of X. So if we write down the equilibrium constant expression for this reaction, it will be K equal to the, the product of both the reactant concentrations. So since both the product concentrations, and since the reactant is a solid here, that means we don't need. Now um, now we are given the reaction vessel volume as 1.5 liter, and it is said that 0.05 gram of BCl3 is added to the container. That means, so we have to find out the concentration of BCl3 for the added amount of BCl3, and that will be also added to this initial concentration of BCl3. So right now this is the initial concentration of both pH3 and BCl3. And now since you're adding an extra amount of BCl3, which is 0.05 gram, that means we have to calculate the concentration for this. So first we have to find out the number of moles of BCl3 for the added mass of BCl3. That will be 0.05 gram over the molar mass of BCl3, which is 117.7 gram per mole. So this will give us the number of moles of BCl3, and then multiplying that number of moles of BCl3 and then dividing that by number of and the volume of the solution, which is 1.5 liter, we can find out the concentration of um, the added BCl3, and then it will be 2.84 times 10 to the minus 4 molar. So this is the concentration of the BCl3 added. That means the total initial concentration of BCl3 will be this concentration added to the initial concentration calculated. So it will be 0.0084 molar plus 2.84 times 10 to the power minus 4 molar, and the summation will give us 0.0087 molar. This is the initial concentration of BCl3, including the mass of BCl3 added. So now we know the initial concentration of both the products. Now we have to set up the ice table for this reaction. From there we'll be able to find out the equilibrium concentration of pH3. So since our reactant is solid, we don't need to include that here in our ice table. We'll just add our gaseous products, and the initial concentration of pH3 we have calculated as 0.0084, and for BCl3 it is 0.0087. Now if we consider the change as y, then the change for both of them will be minus y. And at equilibrium, what we'll have is 0.0084 minus y and 0.0087 minus y. So these are our equilibrium concentrations now. Now we can again plug them in our equilibrium constant expression, which is Kc is equal to both the products concentration, since once again our reactant here is solid, and that's why we don't need to add them here. And the value of Kc we have calculated as 7 times 10 to the power minus 5, and since we know that this value is constant for a given temperature, that means it will be same here at least or unless the temperature is not changed, and the pH3 concentration we have calculated as this 0.0084 minus y times the BCl3 concentration 0.0087 minus y. So if we rearrange this, it will take a quadratic form of y square minus 0.01711 plus 0.3 times 10 to the minus 5. Equal to 0. And solving this quadratic equation, we will have two values for y, that point 0.017 and 0.0018. Now, since 0.017 is greater than our initial concentrations here, that means um, this value is not acceptable and the value of y is this one. So that means the equilibrium concentration of pH3 will be equal to 0.0084 minus y, 0.0084 minus 0.0018 mole per liter, and from here we get, okay, so this value here is 0.0008, and so, and this will give us a value of 0.0082 molar solution. So this is the equilibrium concentration of pH3.